Hello everyone, thanks for coming to our presentation. Our research paper is a butterfly core community search over label graphs. My name is Zheng and I come from Baidu. This is a joint work with Hong Kong Baptist University and Rutgers University. Communities naturally exist in networks such as chemistry and social networks. Our studied problem is about community search. Given a set of query nodes, find the densely connected communities containing them, which is user-centered and personalized search. We aim to find out the cross-group communities over label graph. The label graph advertises associated with labels. The figure is an example of IT professional networks, where each vertex represents an employee. The labels are the employee roles, such as software engineer and product manager. The solid edges denote the collaborations of the same role, and the dashed edges represent the collaborations across over different roles. The input are two query vertices from two labeled groups. We define a new butterfly core community model for cross-group search, and the result is shown in the right. Its structure meets three criteria. First, the participation criteria requires the result to contain input queries. Second, each group is cohesive linearly. Here, each vertex in subgraph L has at least 4 neighbors. It's similar for subgraph R, in which each vertex has at least 3 neighbors. Third, these two groups, L and R, are well interconnected with cross-group interactions, denoted by the dashed edges. Actually, it forms a 2-2 backlinked in the bipartite graph. The minimum diameter makes vertices in the community are high related to the queries. This helps remove unrelated vertices far away with queries such as U6. The related works to ours include attributed community search, which find vertices share homogeneous query attributes. There are several recent studies on heterogeneous information networks, which are based on metapaths. The previous works on butterfly counting focus on the global number of butterflies contained in the bipartite graph. We model the cohesive structure inside each group by k-core, which means each vertex has at least k neighbors. The coreness is the largest number k, such that there exists a connected k-core containing the vertex. In the bipartite graph, the vertices site can be partitioned into two distinct subsets L and R, and every edge connects a vertex in L and R. The butterfly is a 2-2 backlink on the bipartite graph. Butterfly degree is the number of butterfly subgraphs containing the vertex. In the example graph, 2,3ZW forms a butterfly. The butterfly degree of vertex 2 is 7, since there are 7 butterflies containing the vertex 2. We have considered several traces to model cross-group interactions. The first one asks each vertex in the result has large enough butterfly degree. However, some vertices mostly link within their own group with less interactions across the groups. They will be missed. Second, we consider a global criterion that the total butterfly count is large enough, which is also commonly studied before, but it's hard to estimate a qualified number of butterflies in advance, since it varies significantly over different kinds of graphs. Finally, motivated by real applications, we select the third one. Only exists at least one vertex in each group whose butterfly degree is large enough. One collaboration community usually has at least one leader in each group, who are in charge of communications across the groups as leaders or liaisons. Then the BCC model could search with input query vertices, no matter they are leaders biased or juniors biased. In other words, with or without cross-group edges. This is our butterfly core community model definition. The vertex set could be split into two distinct sets with two labels. Take the figure as an example. There are two subgraph parts, L and R. The left is a K1 core and the right is a K2 core. There exists a vertex on each group with butterfly degree no less than B. Here we set B equal to 1. Butterfly is a good choice to model the interactions between two groups, as it's a fundamental motif in bipartite graphs. Take an example in the user's items bipartite graph. Two users buy the same two items, which will form the butterfly. The more same purchase indicates the more similar preferences. The BCC model enjoys high computational efficiency. considers different group densities and could automatically identify the leader pair. The figure shows one example of the BCC search result given these inputs. The output is a connected BCC with the smallest diameter, which is shown in the right. The BCC problem is NP-hard, which is reduced from the maximum click. We also prove it cannot be approximated in polynomial time within a factor 2 minus epsilon of the optimal. We propose a basic BCC search framework. First, it finds a maximum connected BCC containing queries, then iteratively removes vertices with a maximum distance. Meanwhile, maintain the remaining graph as a BCC, keep each group as k-core, and apply butterfly counting to check there exists one vertex on each group with larger butterfly degree. Repeat these steps until no longer possible. Finally, return the BCC with the smallest query distance among all generated candidate graphs. This basic BCC online search framework achieves two approximations to an optimal, which takes big O T multiply the sum of du squared plus edges number. To improve efficiency, we first propose the first query distance computation. Instead of computing the query distance for all vertices after each phase of graph removal, we identify a partial update. Dmin is the minimum distance of vertex in the deletion set to the query queue. We analyze the vertices with distance no larger than dmin keeps unchanged. Also for other vertices, their distance are monotone non-decreasing. Generally, we identify the vertices need to update and the traversal starting points in BFS. The leader pair identification is to find a good pair of leader vertices whose butterfly degree are large enough even after a number of graph removal iterations to decrease butterfly counting times. They need to have large butterfly degrees and are close to query vertices. The leader pair identification searches from the query vertex in a BFS manner until find one with butterfly degree no less than a threshold. Take an example to search in the left group. It initializes P whose butterfly is not large enough, then search among queries, one hop neighbors. Finally, select V1. We also need to solve how to update the butterfly degree of leader vertex during the graph removal, which deals in two cases according to the labels of leader vertex and delete vertex, the same or different. Then update based on their common neighbors in slightly different methods. The local method is very efficient, especially in large graph dataset. The candidate graph G0 is really small. It first finds a path connecting the queries, then iteratively inserts adjacent vertices until size exceeds a threshold. We extend the model and algorithm to multi-label BCC search, which supports multiple labels of input queries. The MBC model contains multiple label groups. Each group is a k-core, and the cross-group connectivity ensures any two groups are connected by cross-group interaction directly or through a cross-group path. We conduct experiments on 7 real-world networks with ground truth and synthetic communities. For effectiveness, we compare with two baselines. Our three methods are implemented with different algorithms. We find our methods achieve better F1 scores on the datasets. In terms of efficiency, our L2P BCC achieves the fast processing query time. The ablation studies validate the speed up of query distance and butterfly computations, which significantly reduce the times of butterfly counting. We conduct a case study on flight network where each vertex represents a city, label is their home country, and inner group edges are domestic airlines, and the cross-group edges are international ones. In our BCC result, the blue left is a 6 core in Canada and the red part is a 5 core in Germany. The 4 yellow vertices indicate one butterfly. The L2P BCC method outperforms the baselines on F1 score varying the number of labeled groups. This is an MBC case study on the collaboration networks. The 3-labeled BCC on the right is an interdisciplinary community from database, machine learning, and system research field. In conclusion, we study a new problem of BCC model for cross-group community which is NP-hard and cannot be approximated within a factor of 2 minus epsilon of the optimal, and extend to MBC model for multiple label queries. We propose a 2 approximation framework and develop several algorithms to improve efficiency and conduct experiments on real datasets. Thanks again for coming to our presentation.